Hello and welcome back. We are showing that n to the 4 minus 4n squared is not going to be in big O of n cubed. In the previous video, we did another exercise very, very similar to this one. So I'm going to recommend you watch that one before you watch this one, because I do take a couple of shortcuts here, like not fully writing out the whole definition of big O and its negation in my pursuit to prove this to be a true statement. So to prove this to be a true statement, I do want to put this in some logical notation. So it would be mathematical notation. It would be something like this. For all m greater than 0, for all n not greater than 0, there exists an n greater than n naught, such that n4 minus 4n squared is going to be strictly greater than m times times n cubed. Okay, and once again, we're going to notice that we have that difference of squares, or sorry, difference of terms right here. And so that tells us once again that we're going to want to do that factoring out. So we take out that n to the 4, and that's going to leave us with 1 minus 4n squared, less than or equal, or sorry, less than, greater than m times n cubed. All right, now here, unfortunately, unlike the previous one, we have a 1 here, which means that we cannot make sure that this is less than 1. That won't be sufficient. We have to make sure that this is less than a half so that we can round up to a half. Now, 4 over n squared needs to be less than a half. And so what I know for sure is as long as my n squared is greater than 8, I won't have a problem here. As long as my n squared is greater than 8, because 4 over 8 is a half, we're going to be good. So by that same lazy logic as previous questions, I'm just going to go ahead and say, make my n greater than 8. I just need to find that there exists. I don't have to find the tightest bound, so this is just fine as is. So given that that is going to be true, that n is definitely greater than 8, I can rewrite this as follows. N squared greater than n to the 4. This will just be like 1 minus a half, so this will just end up being times a half, which is going to be greater than m times n cubed. Okay, so now that we have this in mind, we have picked a reasonable value of n so far. So now at this point in time, we need to still make sure that we consider our n naught in here somehow, and we consider our m in here somehow. So just as we said in the previous question, and is a very common occurrence, we want to make sure that our n is going to be strictly greater than n naught plus 1, because we want to make sure that we're pushing our n above that fractional space that just drives us absolutely bonkers. So we want to make sure that it's at least this big. And you'll notice that n greater than n naught plus 1 and n greater than 8 are sort of the same. The key being you do actually have to mention this n naught in your function. Otherwise, we're sort of leaving gaps and it's not as mathematically rigorous. As it was brought to my attention in class, somebody asked, oh, well, could we do something like this instead of having two terms? Could we just do something like this, where we effectively force it to be greater than 8 is greater than n naught? I guess we'll say 8 is greater than n naught plus 1, and 8 is greater than 9, or n is greater than 9, or n is greater than 8 in this scenario, then that's also totally fine. You could combine them like that, and that would also still be a fine solution. You just have to make sure that in your n value that you take into account that n naught. We didn't lose that here. That's acceptable. Okay, so with that in mind, we still need to figure out how to think about this in terms of m. So at this point in time, we have n to the 4 over 2 is greater than m times n cubed. And just as we've done previously, we want to try to get n isolated and figure out what n means in terms of m. Let's multiply both sides by 2. We end up with this. And if we divide both sides by n cubed, we will have n needs to be greater than 2m. And so now we have figured out the 2 to 3, depending on how you write it, bounds that you want to focus your n in on. So we can say let n equal to the maximum I'm going to keep mine in the 3 terms, but we could combine these two if you wanted to, as we said. N naught plus 1, 2m, and 8 plus 1. And in doing so, we can observe that n is greater than the maximum between those 3 values without the plus 1, 2m, and 8. And now we're able to continue with our proof at this point, where we can notice that when n is greater than 8, this up here will hold, this will hold true when n is greater, oh God, when n is greater than 8, this holds true right here. And then when n is greater than n naught plus 1, as the same as when it's n is greater than 8. So if you combine them, you can say that we know that we're living in that non-fractional space. We don't have to worry about the fractions like messing up. Whoa, that was weird. Messing up something like this and suddenly ending up with a value that could potentially cause problems there or there. And then we can also say that we can observe that n is greater than 2m, which allows us to prove this point right here. And once you've done that, you're able to then put it all together so that you can say n to the 4 minus 4n squared was greater than n to the 4 over 2, which was greater than m times n to the cubed, m times n cubed, which proves that n to the 4 minus 4n squared is definitely greater than n times m cubed. And that's all there is to it. So it's not terrible. It is very formulaic. Wow, it must be a Friday afternoon. And we can sort of see how we can walk through these proofs to determine whether or not something is an order of another function. Okay, so that's all for this one. After this, we're going to take a look at some warm-up questions, sort of practice multiple choice questions. And then after that, we will break into some theta proofs and some little o and little omega proofs as well. Thanks, everybody, and have a fantastic day.